Brand new chapter we're starting today, possibly even finishing today. It's a pretty quick one, Chapter 5, Chemical Reactions. It may be a quick one. It is also an important one. So chemical equations, chemical reactions are going on all around us. Sometimes we can express them, or we do express them just as words. So on exam 1, we had an example of this with methane gas reacting with oxygen to produce carbon dioxide and water. That was described to you. You didn't have to put down the actual chemicals. Chemical equations are just our way of summarizing what's happening in a process. So two things interact together. We're not thinking about how they interact together, just these two things react, and out pops these other two things, or out pops one thing. Again, not focusing on the actual, like, what's happening. You can take OChem if you'd like to learn about that. But our general form is we've got our reactants, that's our left side, the things that react, and those turn into our products, the right side. I'll often use those interchangeably. And we've got a single headed arrow in this case that indicates the direction. You might be thinking to yourself, aren't they all going to be left to right arrows? We're never going to see a right to left arrow, surely. Sometimes we will see left to right and right to left at the same time. So we'll see like a double arrow. That means that the reaction can go back and forth. We will see those occasionally. Even when we have that double-headed arrow, we still call the left side the reactants and the right side the products, even though the things on the right side can go back to the left side. Some examples of word equations. One example would be, I dropped my phone. It hit a rock, and now my screen is cracked. So phone screen interacted with rock, and out came cracked screen and perfectly intact rock. The example that we saw on the exam, methane plus oxygen reacting together, like if you're burning gas at home, to form carbon dioxide and water. Our chemical equations represent reactions. So again, the things on the left are the reactants, the things on the right are the products, and we often indicate the state of matter in parentheses after the formula for each chemical. So in this case, these are all gases. So G for gas. We'll also see S, L, and AQ. And I think we have a table after this, so I'm not going to go through those yet. Generally, when we see chemical equations, we're going to express the chemicals as their chemical formulas. Rather than writing out the whole word. If you get good at nomenclature, once you've learned how to read all of these formulas and turn them into their names, you can read it left to right, straight across, and it takes about the same amount of time, even though they're in their formulas. At least for the ones in this class. If you get to other chemical reactions, you'll see stuff and you're like, I have no clue what that is. And that's what Google's great for. All right, so we're going to express our chemicals in their formulas. And generally, we'll see either a skeleton equation or a skeletal equation that just shows formulas. There's other things that we would also want to put in to make it not a skeletal equation. So it's a skeletal equation because it's just the bare bones. It's just the very basics of what you need to have an idea of what the equation is. But we don't know how many of each thing are reacting. So this would be like somebody telling you that they've got an awesome biscuit recipe. I mix water and flour and I bake it. Cool recipe. Now I can make it too. Right? No. Like they've told you what goes into it. Like, okay, I've got those things at home. Tell me more. Tell me like how much water do I need? How much flour do I need? Like what are the other process steps involved? So like the skeleton equation, the skeletal equation, just the absolute minimum, like what are we putting into this thing? And we'll buff that up with some more information. Other things that show up in our chemical equation. We've got S as a symbol for solid, L as a symbol, I don't know why I had so much trouble with that Q, for liquid, G for gas, AQ for aqueous. Aqueous meaning dissolved in water. And typically, the symbols are like in italics, so they're like slightly slanted over. I'll usually write my L's as like a cursive L. It probably doesn't matter. So that's what those things mean. And then, of course, we've got our pluses to indicate that we're separating things out. Okay, so adding and upgrading from our skeletal equation, adding more information, is a balanced equation. So this is what that skeleton or skeletal equation looked like. And we've got some space-filling models of the chemicals shown. So for our CH4, that's methane. We've got one carbon in the middle, that's the black one, and then the 4 white hydrogens on the outside. Our O2, we've got 2 red spheres representing each of our oxygens and so on. And if you just look at the red balls, right, we've got 2 oxygens on the left side. We've got 1, 2, 3 oxygens on the right side. And this is not allowed. This is illegal. Why is it illegal? It's not balanced. Why does it have to be balanced? Matter can't be created or destroyed. I am not a magician. I cannot just simply pull one of these red balls out of a hat, out of my pocket, out of thin air, right? I don't have, they're not like tucked into the folds of my hands. So atoms cannot simply appear or disappear. What this means is we must have equal number of each element on both sides. So we've got carbon, hydrogen, and oxygen. Those are the 3 things showing up in our equation. We need to have the same number of carbons on the left side as we have on the right side, the same number of hydrogens on the reactant side as we have on the product side, the same number of oxygens on both sides as well. Any questions so far? All right, we've got some steps that we can take. So to correct the problems of our skeletal equation not being balanced, we can create a balanced equation. There will be times where you're not told that it's an unbalanced equation, or you're not told that it is a balanced equation, and you'll have to check whether it is or not. An equation is usually balanced if it has numbers, coefficients. So we'll be putting numbers in front of some of these, and we call those coefficients. So sometimes you'll be provided an equation. If it has numbers in any of these blue spots, that usually means that it's balanced, but it's always a good idea to just go ahead and count through and check if you're not sure. Okay, so we also have another imbalance. We've got 4 hydrogen atoms to 2 hydrogen atoms on the right side. So that's another thing that is not quite in balance. The only thing here that is balanced is we've got the right number of carbons. 1 carbon left side, 1 carbon right side. So let's take some steps to balance it. We're going to insert or change the coefficients. So the number in front of our chemicals, we are not going to adjust the subscripts. So subscripts, all these things that I'm underlining in green. If you change any of those subscripts, you've changed the reaction. For some of you that have some baking mishap experience, you may have been trying to follow a recipe and it called for baking powder and you put baking soda in instead. And those are not the same thing, and so you maybe ended up with a really bad recipe. Or you have unlabeled white powders in clear containers just in your pantry. And I need a little bit of sugar for my recipe. I need a 1/4 cup of sugar. And you spoon out a 1/4 cup of salt and throw that in your recipe, and ooh, really bad cookies, right? We don't want to change out any of our ingredients because that changes the recipe. So we're not going to change the coefficients. Changing any of those changes the chemicals. Different reaction. We can, however, change the proportions. So we can have a little bit of extra water. We can have a little bit of extra oxygen. We can adjust the number of those that we've got playing around. That's all good. So changing coefficients is good. Changing subscripts is bad. But how do we do this? So there's a couple of steps. These are not all of the steps. The first step, you won't always have to do this first step. Determine the correct chemical formulas. You'll have to do this because sometimes you'll be provided with the names and you get to turn those into chemical formulas. So if you're provided with names and not formulas, or if you're not given a skeletal equation, you'll have to do that step 1. You might also be told name and formula, and then you can skip straight to step 2. So just writing out the skeletal equation. You'll need to separate and identify your reactants versus your products. So figuring out what goes on the left side of the equation, what goes on the right side of the equation, based on what you're told in the sentence. Usually it'll say like hydrogen gas reacts with nitrogen gas, and then it'll have like to produce or and produces, right? Some indicator that that's where a reaction arrow goes, and then it'll say like ammonia after that. So there's usually signal words that indicate what our reactants and products are. Then comes the actual balancing steps. So when we're doing the balancing, the fastest way to do it is find an element that occurs in only one compound on both sides. And we're going to balance that first. If we have multiples, then we're going to balance metals first. We will see examples of going through these steps. So if it appears on both sides and it's only in one compound, we're going to balance that first. Because there's probably going to be some other elements with those that are going to change as well. And so it's ideal if we can get all of those big changes out of the way first and then work on some of our smaller pieces afterward. So our next step after balancing that is to balance a free element something like N2, H2, O2, maybe a metal, something where it's just that one element. Because we can change the coefficient on these things when they're by themselves. We can change the coefficient on that to whatever we want, and it's not going to affect something else. So we can change this one for free without ruining the work that we've done already. And sometimes when we do that, we will end up with coefficient fractions as part of the balancing process. We will need to get rid of coefficient fractions. Before it's balanced. If I was smart when I prepared these slides, fingers crossed, we've got an example where coefficient fractions show up. So we'll see that happen. So if we do have a coefficient fraction, usually it'll be something like, it might be like 7.5. And that half doesn't really make sense because you can't have half of a piece of something when we're talking about atoms and molecules. So we would have to double everything to get rid of that half, and we would multiply the entire equation by 2. So all of the coefficients go up by 2 to get rid of that coefficient fraction. All right, let's finish up our list. The last thing that we would want to do is check. It's entirely possible that we make some addition or multiplication mistakes in our head when we're doing this, or plugging numbers into our calculator, depending on how you choose to do it. And so counting up the total number of each type of atom on both sides be helpful, just to make sure that we did actually balance it before we start to do calculations with it. And then again, in summary, do change the coefficients. So like if we put a 2 in front of methane, CH4, that would be changing the coefficients. We can do that. You do not want to change the subscripts. If you change the subscripts, you're changing the chemical. It's a different thing. It might be true still, but it's a different chemical equation. You won't get the right answer, most likely. And again, our goal is perfect balance, harmony between the four nations. All right, so let's go through those steps. Write a balanced equation for the combustion reaction of gaseous C2H6 and gaseous oxygen to form gaseous carbon dioxide and gaseous water. So we're given most of these with just the name and not the formula. So we have to figure out what all these formulas are. I'll do steps 1 and 2 sort of together, putting the skeletal equation together while we do the names. The first one that we were given is this C2H6. This is one that you wouldn't be expected to name for this class. That's ethane, methane's big brother, propane's little brother. So we've got C2H6, and we are told that it is gaseous. So we put a little G for gaseous behind it. We also have gaseous oxygen. What are we going to put in for oxygen? O2. Why are we putting in O2 instead of just O? Brinkelhoff, H7, horses need oats for clear brown eyes. Any of those mnemonics? Helping us remember that in their normal natural states, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, all of those elements in their natural existing state is a diatomic molecule. So there's two of them together. So O2, that's how oxygen normally exists. You can find it in just O by itself or like other funky states, but normally it's just O2. So O2, and that's gaseous. And then we've got the words to form. To form here is indicating our reaction arrow. It's indicating the things that come next, those are the products. And they are also gaseous. We have carbon dioxide. This di prefix lets us know we've got a molecular compound. Also carbon and oxygen, both nonmetals. So we've got a molecular compound. We've got one carbon because we omit the mono prefix, so it's CO2. And again, that's gaseous. And we also have gaseous water, and water's formula is H2O. Questions about putting together the names or the skeletal equation? All right, the next thing that we want to do is we want to balance something that exists in just one thing on both sides. I usually just take a look left to right, so starting off looking at the carbon in our C2H6. Carbon's in only one thing on the left side. It's also only in one thing on the right side. Conveniently, hydrogen also only in the C2H6 on the reactant side and only in the H2O on the right side. So we're going to balance, I'm going to start at least with carbon. Usually the way that I'll do this is I just write down the thing that we're balancing underneath the reaction arrow. We'll write out how many we have on the left side, how many we have on the right side, and then step by step work through balancing things. So with our skeletal equation, we've got our 2 carbons in our C2H6 and 1 in our CO2. We need to increase the amount of carbon that we have on the product side, the right side. So if we add a 2 in front of our CO2, that'll bring us up to 2 carbons. So our carbons are balanced. Then we want to move on to the other thing that's in only one compound on both sides. That's our hydrogen. So our hydrogens, we have 6 hydrogens on the reactant side. We have 2 hydrogens on the product side based on the coefficients that we have. So we need to balance that out as well. Again, we're missing stuff on our product side. So to get up to 6, what do we need to multiply 2 by and put in front of our H2O? That's right, it's 3. So we need 3 H2Os. If we have 3 H2Os, 3 times 2, 6 hydrogens. So our carbons are balanced, our hydrogens are balanced. The last thing to balance is oxygen. So for our oxygen, currently, we just have these 2 little oxygens in our O2. On the product side, we have a coefficient of 2 and a subscript of 2 in CO2. So we've got 4 from our CO2. We've got 3 for a coefficient and 1 for a subscript in H2O. So we've got another 3 oxygens for a total of 7 oxygens on the product side. So we need to figure out a coefficient that we can put in front of O2 that will give us a total of 7 oxygens. What's that coefficient going to be? It's going to be 3.5. So if we put a 3.5 in front of our O2, 3.5 times 2, or 7 over 2 times 2, that's a total of 7 oxygens. And then there's one more step to do to get it balanced, aside from checking if we did it correctly. What's that one last step? Yeah, we need to get rid of this 1/2 fraction. To get rid of the 1/2, we'll multiply all of our coefficients across by 2. So we cross out the invisible 1. We've got a 2 there. Cross out our 3.5. 3.5 times 2, we've got a 7 there. Cross out that 2, we've got a 4. 3 turns into 6. And now, since we doubled everything, we doubled all of our coefficients, that should double the number of all of our elements, so they should still be balanced. And that should be the fastest way to get this balanced. It's not the only way that you can get it balanced. You can just play around messing with the numbers as much as you want until you eventually stumble on the right thing. This way works. All right, and then the last thing that we would want to do is check and make sure that everything's balanced. So looking at our carbons first, we've got 2 times 2 carbons in our C2H6. So 4 carbons. We've got 4 times 1 carbons on the product side. That's balanced. We've got 2 times 6 hydrogens. We've got 6 times 2 hydrogens on the product side. We're balanced. We've got our 7 times 2 for 14 oxygens. We've got 8 and then another 6 for a total of 14. So we're all balanced, even Stevens across the board. Questions about any of those steps? All right. Another example, aqueous solutions of lead-2 nitrate and sodium chloride are mixed. The products of the reaction are an aqueous solution of sodium nitrate and a solid precipitate, or precipitate's just a solid, of lead-2 chloride. Write the balanced chemical equation for this reaction. So this is another type of chemical equation that we might come across. We've got lead-2 nitrate, sodium chloride. These are both aqueous, meaning that they're dissolved. So lead with a 2+ charge, nitrate, NO3-, crisscross it, and we get Pb NO3 2. And that would be aqueous. For our other reactant, we've got sodium chloride. Sodium forms a 1+ charge. It's one of our alkali metals. Chlorine forms a 1- charge when it's chloride. So those will balance each other out. So we've got good old-fashioned table salt, NaCl. That one is also aqueous. And then we're told what the products are, so we can put in our arrow. And our products are an aqueous solution of sodium nitrate. So Na plus NO3 minus, those will balance each other out. So NaNO3, and that is aqueous. And our other product is lead 2 chloride. So Pb2 plus, because of the 2 in lead 2 chloride. And chloride is still Cl minus. So if we crisscross it, we get PbCl2, and it's a solid. So that's our skeletal equation. Questions about getting to our skeletal equation? At this point in the class, this would be kind of towards the top of like hard difficulty for problems. At this point in the class. All right, we want to write a balanced chemical equation for this reaction. So our step 3 from that list of steps, we're looking for something that's in only one chemical on both sides. So our lead is in our lead 2 nitrate. It's also in our lead 2 chloride. Okay. Our nitrate is in our lead 2 nitrate. It's also in our sodium nitrate. Okay. Our sodium chloride has sodium in it. Sodium nitrate also has sodium in it. Our chloride is also in only one thing on both sides. So what do we balance first? Yeah, it's pretty much you balance whatever you want first. So my method for this is for this type of equation, since we've got everything in just one thing on both sides, we pick one that's not balanced. We'll balance that. That's going to change something else. We'll balance that. That'll change something else. We'll balance that. So just kind of like leapfrogging our way as we cause destruction and mayhem until peace is restored in the city. So let's see what that looks like. Our lead is already balanced, so we're not going to worry about that yet. Our NO3 is not balanced. We've got 2 on the reactant side, 1 on the product side. So let's balance that first. So 2 and 1. To balance our NO3, we can put a coefficient of 2 in front of our sodium nitrate. Now our sodium nitrate, our NaNO3, is balanced. Or sorry, our nitrate is balanced. When we add this coefficient of 2 in front of sodium nitrate, the other thing that changes is the sodium. So that's what I would choose to balance next. So let's change the number of sodiums. So we're going to balance sodium next. Okay, so sodium. We just changed the product side to have 2 sodiums. On the reactant side, we just have 1 sodium. So we'll balance our sodium on the reactant side. Put a coefficient of 2 in front of NaCl to get our sodium up to 2. So now our sodium's balanced. When we balanced our sodium on the reactant side, we changed our chlorines, or our chlorides. So that's what I would choose to balance next. So Cl, you've got 2 on the reactant side because we just changed that. And on the product side, our lead 2 chloride already has 2 chlorines in it. So that's balanced. And then the last thing to do would just be to check if our leads are balanced. And our leads are balanced. We've got 1 on each side. So everything's all squared away, nice and balanced. So this is a different type of kind of balancing experience compared to the first one. You'll see the first one more often, but we will come across this type of equation with some frequency in the class. Questions or confusions about any of the balancing stuff? Why did we do that one first? Why did we do this thing in that order? Okay. Now that we're having tons of fun, I've been having lots of fun. I want you to have some fun too. So here's a chemical equation for you to balance. I'll give you like 5 minutes, and then maybe after 2 minutes, actually I don't know how long this one takes, but somewhere in the range of 4 minutes, 5 minutes. And then after a little bit, if you're struggling with the nomenclature, I'll just go ahead and write in the names for you. All right, so we've got the skeletal equation up there. If you were having trouble with getting started, go ahead and work on the balancing part. All right, so this chemical equation is pretty similar in terms of the style of balancing that we're going to do to the previous example that we did. So we've got everything is just showing up in one thing on both sides. So we're going to find something that's not balanced. We scan left to right. We don't have any coefficients other than this 4 in sulfate. On the reactant side, our first kind of new coefficient shows up in the lead 2 iodide. So we're going to balance iodine first. At least that's what I'm choosing to do here. So we have 2 iodines on the product side. We've only got 1 on the reactant side. That's a problem. So we're going to balance that out by adding a coefficient of 2 in front of the Ki on the reactant side. When we do that, the potassium gets disturbed. Right, so now we have an imbalance. We just changed our potassium number on our reactant side, so we're going to look at balancing that next. We've got 2 potassiums on the reactant side, and we also have 2 potassiums on the product side. So that's already balanced. We've kind of reached the end of the road. That was quick. Last thing to do is check our other groups. In this case, SO4, since that's a polyatomic group, an oxyanion, that whole SO4 chunk stays together. We can treat it like one thing. So for SO4s, we've got 1 on both sides. And then our last thing to look at is lead, Pb, and we also have 1 on each side. So our leads are balanced. Questions about any of that? All right. Another exercise for you, one for you to try. This is more similar to the first one that we did for the example. And this one starts you off with the skeletal equation, so you get to just jump right in with the balancing. So give that a shot. All right, so starting off with this equation, what we want to check is something that's in one compound on both sides. And in this equation, that's going to be hydrogen. So we want to balance our hydrogen first. Our hydrogen, we have 2 on the product side because of the subscript of 2. We've got 1 on the reactant side since there's no subscript on the H in HCl. So to balance that, we'll bump up our numbers on the reactant side, add a coefficient of 2 in front of our hydrochloric acid. And then we can balance oxygen or chlorine. It doesn't matter which one you balance first. I'm going to take a look at the chlorine first. So our chlorine, we've got a coefficient of 2 in front of HCl, so that means we're going to have 2 chlorines. And on the product side, we've got Cl2, chlorine existing in its natural state. So we've got 2 chlorines on the product side. That leaves us with one last element to check, oxygen. So for oxygen, we've got a coefficient, or a subscript rather, of 2 on the reactant side. And we've got 1 H2O, that invisible subscript of 1 for our oxygen. So 1 oxygen on the product side. There's 2 ways that we can try to balance this. One of them is faster. Who's got an idea of how to balance our oxygens? Yes?
You would add a coefficient of 2 in front of the H2O, and in doing that, you would have to change some of the coefficients for something.
Right. So one of the options that we have is we can bump up this 2 in front of our H2O. That's going to change our H. So then we'll have to change the H on the other side, which means that we've changed our chlorines, which means that we have to add another thing in front of our chlorines. So there's a couple of steps that we have to do if we do it that way. let's wind the clock back a little bit. So that's one of the methods that we can do. The other method that we can do is we can put a coefficient of 1/2 in front of our O2. This is the less intuitive way of doing the problem. This is probably not the first thing that came to mind. Most of you probably, I'm guessing, just didn't even think of it. 1/2 with our coefficient and 2 for our subscript. We now have 1 oxygen on the reactant side. But we've introduced a new type of problem, right? We have a 1/2 for a coefficient, so we have to get rid of that. The way that we get rid of that, we multiply all of our coefficients by 2, and then it'll be balanced. So this ends up giving us the same result, but it's fewer steps of jumping around, bouncing between each of our different compounds or chemicals. You can do it the other way. That still gets you to the right answer, but with more steps, more multiplication, more addition, there's just more spots for you to make a mistake. So I'm not going to tell you you can't do that first one that I showed you with the just changing everything one step at a time. But if you're comfortable doing it this way, if this feels okay to you, then I would recommend doing it this way. Won't come up very often. We're giving you weird ones for our in-class exercises. Okay, any questions about our balancing exercise there? Great. Okay, so some other things that we can do with reactions, other than just balancing them, there's like different types of reactions, different classes of reactions. And our 4 basic categories of reactions are listed here, and we're going to go over them individually. They should be on their own slides. So these are, how to describe it? It's kind of describing like what's going on without describing really like what's involved. So a combination reaction, we're adding 2 things together and they just combine and it makes one product. A decomposition reaction, it's breaking up. So it's kind of like how are things moving around, not really like what's involved necessarily. So we'll see examples of these. There's also a couple specific types of reactions that we'll learn. So a combination reaction, for a lot of these generic things, we're just going to be using like A, B, and C, and D, just to stand in for chemicals. These are actually elements in this case. And those are combining to form a compound. It's not always going to be elements. It could be small compounds that smush together. And we could also call this a synthesis reaction. And an example of a combination reaction is the soft, squishy, rather dull sodium metal reacting with toxic chlorine gas to form sodium chloride table salt. These like general classes of reactions, if you like flashcards, great flashcard material. Combination reaction on one side. On the other side, A plus B goes to AB. Flip, flip, flip. Easy practice. Our next type of reaction is the decomposition reaction. So our chemical AB here is decomposing, it's breaking down into A plus B. So it's decomposing or breaking down rather than combining things. So these are kind of the opposites of each other. a lot of these will involve some sort of input of energy, because usually to get something to break up, you need to put some energy in unless it's really unhappy. Then you might only need to put a little bit of energy in. So carbonic acid decomposes, for example, to form carbon dioxide, and it also forms water. So if you pressurize, add a bunch of CO2 into a can of soda, you'll form carbonic acid in there. That's one of the ways that it can store CO2. And that can decompose to form carbon dioxide and water. So there's an example of a decomposition reaction. You don't need to know these specific examples. The examples are there so you can see it like with chemicals instead of just letters. A combustion reaction, this is one of our specific reactions. That you were promised earlier. So a combustion reaction involves a reaction with oxygen. So O2 as a reactant, as gas, to form heat and light and some other stuff. So the heat and light are not written usually in our reaction. For most of the things that we'll be doing in this class, our products are going to be carbon dioxide and water. So the key points for a combustion reaction: one that you should know, it produces heat. That's usually why we're doing combustion reactions. And then the important chemical details. An oxygen reactant, CO2 and H2O as products. So if you wanted to make a flashcard of this, right, you'd put O2 reactant, CO2 and H2O as the products. That's going to be true for this class. It's not true for every single combustion reaction. It's just substances that are carbon and hydrogen, or carbon, hydrogen, and oxygen. So things like propane, which is C3H8, that you'd use for grilling outside. That's going to be true for octane and other hydrocarbons that show up in your gasoline. That's also going to be true. So if you've ever seen somebody start driving after they've been sitting at a stoplight for a little bit and you see water coming out of their tailpipes, this is where the water's coming from. Water vapor that is produced from the combustion reaction in their engine, condenses in their tailpipe, and just rolls out as they zip away from the light. Questions about combination, decomposition, combustion? All right, an example. This is something that you might get. Again, a harder question probably on an exam, one that I would expect fewer people to get. Octane is a component of gasoline. Write the skeletal equation for the combustion of octane, then balance the equation. On an exam, it would be more like, what's the coefficient of oxygen in the balanced equation? So you'd have to come up with the skeletal equation, you'd have to balance it, and then you'd have to choose the correct coefficient. So for this, we're given octane. To complete the skeletal equation, we need to remember what our other reactant is. It's O2. All fires need oxygen to breathe, just like us. And then we also need to remember our products. One of our products is CO2, not great for breathing. And our other is H2O, water. Then we go through the work of balancing the equation. So we're going to pick something that's in one thing on both sides. So carbon, for example, and hydrogen as well. So we can balance everything up against our C8H18, our octane. So balancing our carbon, we currently have 1 carbon on the product side. We got to get that squared away. If we add a coefficient of 8, that'll bring our carbon count up to 8. We also balance our hydrogens. We have a whopping 18 hydrogens in our octane. And we've got, so far, 2 hydrogens on the product side. So we'll need a coefficient of 2, or of something in front of our H2. 9 would work for us, since 2 times 9 is 18. So we add a coefficient of 9 in front of our H2O. Now our hydrogens are balanced. Then the last thing that we need to balance is our oxygen. We have 8 times 2, 8 coefficient, 2 subscript in our CO2, and 9 times 1, so 9 oxygens on the product side. So 16 plus 9, 25 on the product side. On the reactant side, it's just from the coefficient of 2 on our O2. And now we need the number that we multiply by 2 to get 25. (25/2) fits that. That's the same as 12.5. So this is another one of those cases where we end up with a coefficient, and then we double everything to get rid of the coefficient. So 2, 25, 16, 18 would be our final coefficients. Question?
So when you have a half, is it always just multiplying all the subscripts by 2, or does that number everything?
Yeah, when it's half, we'll always multiply by 2. You could multiply by 4, and that would get rid of it, but then you would need to simplify everything down, so then you would divide by 2. So yeah, multiplying by 2 is the way to go. Not all combustion reactions work out with coefficients. I've just chose all the ones, only ones that did. So we get in the habit of it. Question?
So if we're given a problem like this, where it's a combustible chemical, and we're given that it's a combustion reaction, you have to know that oxygen is a reactant and CO2 is 200 products.
Correct.
Okay.
This would be a fair game question on the exam. You need to know oxygen reactant, CO2, H2O for products. It's one of a small number of reactions that you actually have to know for the class. All right, getting back to our types of reactions. Another type of reaction is a single replacement or single displacement. Reaction. A single replacement or single displacement reaction occurs when we've got a chemical replacing another chemical. So in this A plus BC, A and C are getting together, and B's sitting out lonely. So A swaps with B. And this would happen, for example, when zinc or another metal reacts with an acid to produce hydrogen gas, H2, and a salt. A salt, that is a salt, is an ionic compound. There's a difference between a salt and salt. Salt is sodium chloride, table salt. A salt could include salts, but it could be like zinc chloride. For example. Our last class of reaction is the double replacement reactions. So this was that like other type of balancing that we were doing, and this is the partner swap. So in this case, we've got B and D swapping to produce a new partner pair. Again, this could be called a double displacement reaction as well. I think one of our labs has it written that way. A type of double replacement reaction, probably the most common one that we'll see, is called a precipitation reaction. And our definition for a precipitation reaction is here. So we have two aqueous solutions. So two solutions, two sets of things that are dissolved in water separately. So we have got one solution, it's dissolved, we can't see the particles. We've got another solution, it's dissolved, we can't see the particles. You mix them together, and it forms a solid. I'm drawing the precipitate in here as these red dots. And the name for that solid that comes out is called the precipitate. Mostly unrelated to chemistry, what would we call snow, sleet, hail, and rain? Who knows what we could call all of those four things? Precipitation, so things seemingly coming out of nowhere or forming out of thin air. Same sort of an idea here. We've mixed two solutions together. We wouldn't have expected anything to happen necessarily, and voila, we've got a precipitate, a solid that formed. And to my surprise, but not my disappointment, we're out of time. So we'll finish this up next time and then start on chapter 6 as well.